male. So we are now on 3061. Okay, so it's and so that's on solubility. It's the first booklet for the 3.6 standard. So we're going to be doing solubility. Johnny, I have put the one up today, so it should be there now. So hopefully it'll work. I've been having a bit of trouble with my downloading, and it's been doing funny things, but it's affecting more level 2 than level 3. Okay, so what I said last week, the very important thing when you have to do the calculations for this section on solubility is you have to work out, do my ions for my insoluble salt, so calcium sulfate or barium sulfate or whatever, do the ions come from a single source? So I've taken calcium sulfate and I've dissolved it in water, so both the calcium and the sulfate come from calcium sulfate, so it's a single source. Or do they come from different sources? So I take some calcium sulfate and I put it into a sodium sulfate solution. Can you see that my calcium comes from the calcium sulfate, but the sulfate comes from two different places? So what I'm trying to say is the calcium and the sulfate have different concentrations. Or I could say I've got some calcium chloride and some sodium sulfate, and if I mix them, then the calcium comes from the calcium chloride and the sulfate comes from the sodium sulfate. They won't have the same concentrations. So I've got the Joe, you had a question because of the O. Just thinking what you meant by that, because that sort of popped up when I was talking about the calcium sulfate being added into sodium sulfate. Okay, the water. No, the water is there just to make it soluble. So it could be any insoluble ion. It could be just, now of course I can't think one, silver chromate or lead bromide or something like that. Okay, so you've just got to say, are my ions and my insoluble salt, do they come just from one source or two? And we will go through this. So if they come from one source, you get a fairly straightforward question, because you can use this Ks is equal to S squared for a AB salt, in other words like calcium sulfate. It's a 1-to-1 ratio between the calcium and the sulfate ions. So that's when I use this formula. So either I can work out my Ks by taking my solubility and squaring it, or if I have to calculate my solubility, I take the square root of my Ks value or solubility product. I know some of you weren't here last lesson, so we will look at as we carry on, and I'll explain what these terms mean. The solubility product, though, for an AB2 salt. Okay, that's a good question, Joe. What is K? K is the equilibrium constant. Now, I don't think you did level 2 last year, if that's correct, so you haven't come across Le Chatelier or anything like that. Basically, when you've got something, a reaction, it's always in sort of tension between products and reactants. So some reactions work all the way, and so if I'm say burn magnesium, it gives off so much energy that all my magnesium reacts with all my oxygen to give magnesium oxide, and I don't have any magnesium oxide breaking up to form magnesium and oxygen again. But others are in sort of an equilibrium between the two. So the bigger the equilibrium constant, which is showing that ratio, the bigger it is, the more the reaction lies to the right, the equilibrium position lies to the right. So for instance, that magnesium and oxygen burning will have a very large equilibrium constant because it goes all to pretty much completion. Yeah. But if I have a reaction like this, calcium sulfate being dissolved in water, it's not very soluble. So most of my stuff is going to remain as solid calcium sulfate, and only a tiny little bit is going to form the calcium ions and the chloride ions. So I'm going to have a very small constant. So that K is just a constant that gives me my ratio. And an equilibrium constant, the only thing that changes it is the temperature. So if you change the temperature, you can change where that position lies. So you know with some reactions it doesn't necessarily work, but you heat it and then suddenly it may start working. Pressure, no, pressure won't change the actual equilibrium constant. So it's only temperature. Right, so if you've got an AB2 salt or an A2B salt, so an A2B salt is like, I'll get back to the A2B salt is something like silver chromate, Ag2CrO4. So I've got 2 silver ions for every 1 chromate ion, or an example of AB2 would be, say, something like magnesium hydroxide. I've got 1 magnesium ion to every 2 hydroxide ions. So when I've got those types of salts, then I use this quick shorthand method. So I take my solubility, cube it, and multiply by 4 to work out the solubility product. Okay, or if I want to work out the solubility, I take my solubility product, divide it by 4, and then I take the cube root. So you need to know how to do a cube root in your calculator. So Joe, I don't want to go into sort of like too much detail on that. We can perhaps have a separate lesson on equilibria, because it is really level 2 stuff, but only the, as I say, the temperature will affect the actual constant value. In other words, where that ratio lies. By changing the pressure and by changing the concentration and so on, you can cause the position to shift left and right, but that's only because you've made those changes. But the actual ratio has to stay the same unless you've changed the temperature. And as I say, that you do a lot at level 2, so I know I'll be doing that in my level 2 lessons, which happen every Tuesday at 11, and you may want to join in with that. I must just remember to show you. Or how are the rest of you? Are you okay with the equilibria? Yep, okay. Right, so that is, as I say, for single source. And you will get a question like this because this is an achieved level question. Because all you have to do, you get given either KS or S, and you have to solve for the other. So it's pretty much write down the formula, plug it in, work it out in your calculator, and give the answer. So there's not too much that can go wrong, assuming you don't make careless errors. Okay, but there's no real conceptual things. So let's look. Why is this not working? There. Okay. Let's look now at other things where you might have to work out what to do. So just as a going over again, remember AB breaks up to 2 ions in a 1:1 ratio. So this is the equation. And this is what we call the solubility product expression. That's your ratio for your equilibrium constant. So there's your equilibrium constant. Because we're dealing with solubility, the equilibrium is all about solubility, we call it Ks, S for solubility. In the next booklet we do Ka for acids, and we do Kb for bases. So it's quite, intuitive. So I have my products over here, and I divide it by my reactants. Now my reactants, because it is a solid, the concentration doesn't change, so I can ignore it. What happens is that sort of gets combined, and when they work all this out, when they work out the case values, it gets combined into the Ks constant. So you'll notice I don't have any products underneath here. I've only shown the reactants because let me do that again. I only have products, I don't have reactants because my reactants are solids. And there should be a square bracket over here. So sorry, I forgot about that. Right, so if I have an A to B, I have twice the amount of A than B. So if my solubility for this salt was, say, 0.1, okay, then 1 of this will form 1 of B minus. So if that's 0.1, then this will be 0.1, okay? But in other words, for every one of this that breaks, that's not actually quite clear. For every 0.1 that breaks up, that'll be 0.1. So if this is 0.1, I'm forming twice of this, so this will be 0.2. So what you substitute in for A plus is 0.2. So you double A and you square it. So it's two things you have to do to it. Whereas for B2 minus, you just put in the 0.1. Okay, so just that we did cover last week. And as I say, this only works for pure solutions when so in other words, from a single source, when we use this shorthand, Ks is equal to S squared. Okay, right. So, as I said, you will be asked to calculate either the solubility product or the solubility as a straightforward question. I'm actually wondering, I've done actually all this last week, so I'm going to, I might just move on. What I want to move on to now is number 3 and number 4. Okay. So let's look at a few questions here. So Johnny, you've watched quite a few videos that use ICE. Is that the International Cambridge exam? Oh, the ICE. Oh, the ICE method. Yes, we do use the ICE method. I particularly use it in the acids and bases, but it is over here as well. I think I've got it in here. Let's just work through it, and then I'll go back to it. So Joe, what is ICE? Initial, the change, C for change, and E for end. So it's when you want to work out, like you started off with this, and you'll use it with these common ions and all that sort of thing, then the change and then the end, and then whatever comes up at the end, that's what you use in your equation. Okay, so just going back to equilibrium again. So Joe, this is particularly important for you, and anybody as a refresher. Remember what I said, there's this tension between the reactants and the solid. And if I change the system, remember the ratio still stays the same in terms of the K value, okay? But if I say add more chloride to the mixture, then the system is going to have to change to minimize that chloride, because remember the K value wants to stay the same. So if I'm adding chloride, I've added a stress or a change to the system, so it's got to try and remove that chloride to make the K value stay the same. So first of all, in equilibrium, the forward and reverse rates are the same. Okay. So what I've said this about removing the chloride to try and keep K the same, the French chemist Le Chatelier was the one that came up with this, and so this rule you learn at level 2 and then you use it at level 3. So if you change the conditions for a system in equilibrium, then the position of the equilibrium shifts to minimize that change, because that whole point is to try and keep K the same. Temperature will do the same thing, although now you're going to be getting a new K value as well. Okay, so an example here was, I've added water to the system. So if I've added water to the system, my concentration of the silver and chloride decreases because I've got more water. So I'm going to get more silver chloride dissolving. Okay, so if this decreases, more is going to go across. Yep, so April, it's only temperature that changes the K value. So as an example here, if we were trying to plug in values to show this, now that's why, by the way, KS values are always quoted at a particular temperature. And if we give you a KS value in the exam, you know, even if we don't give you the temperature, it's going to be for that particular one. Okay. Right, so as an example, if I've got my KS and you can imagine some of it is dissolving, I mean, I could have put this in all in solution up there, but I thought if I separated the solution from the solid, it might make it clearer. So if I was trying to work out my concentration, I've got 2 of those per unit volume here and 2 anions per unit volume. So it's a 1-to-1 ratio, so 2 times 2 is 4. Okay, so if I now, so I've just done it again, but I've added now more silver ions. So I've added a common ion to this mixture. So what's going to happen by Le Chatelier, my stress is adding more silver, so I have to remove, or the reaction has to remove the silver to try and keep the ratio of reactants to products the same. So the reaction is going to position is going to shift to the left, okay, and it's going to keep on doing that until I have the same K value. Okay, so you get more being deposited until, now notice that those concentrations are different, but I've still got the same K value. So so what I've just done is when a silver went, you know, the chlorides will also go. Remember, this whole thing is pretty fluid. You have to, at equilibrium, a reaction doesn't stop. It means I've got continuously reactants changing to products and products changing to reactants. It's just so, as say more deposits, then say another one from over here might dissolve in again. So what's just going to happen in the solution, Joe, is that we're going to get enough silver and chlorides depositing to give us the same constant value. Because you can't have, say, all the silver depositing, because then you, or a whole lot of silver depositing, because you'll end up with, say, too many negatives in solution. So if I added this as a silver nitrate solution, those extra ions, the nitrates are there as a negative, but if I don't remove any other negatives, I'm going to have and I just remove positives, I'm going to, you know, the reaction's going to stop because it's I've got then too negative a solution. So some of the chlorides are also going to deposit to try and keep that. It was, right up here, it was an ionic solution. So I had my silver chloride, I dissolved it in water. Most of it didn't dissolve, but a tiny, tiny bit did. So I really had an ionic solution. And then I added, say, something like silver nitrate, which is totally soluble. So I didn't bother showing my nitrate ions. I've just showed my silver ions. Okay? And those had to, so that this reaction had to move over to the left just to keep my Ks the same. But it's a good point. Perhaps I should redo this showing the other ions so you can actually see I've still got to have the same ratio of positives to negatives because that, you know, is also important. Okay, but that's just the nitrates that I've added. Right, so with Le Chatelier principle, as I said, the more silver's added, I'm going to have the position shifting to the left. Okay, yes, I can see I'll have to perhaps think of how to bring, I mean, chemistry can be very complex, trying to bring it all in. Okay, so, and as I said, for Ks to stay constant when you increase the A plus, Ag plus, you must decrease the Ag2 plus, the Ag plus. And yes, some chloride will also deposit as well, as long as overall my constant stays the same. Okay, right, and because it shifts over to the left, if I can't just have my silver moving over, sorry, over here, my silver moving over, if you think of that equation, there it is, because I'm not just going to get silver ions depositing and I'm just left with all these negative chlorides, they've got to also go back. So the Ag must combine with the Cl on the solid. So can you see that both of these will decrease? Okay, so I had two chlorides, I've now only got one. I had two silvers, I added a whole lot of more silvers, so I've got more than I had before, but I still have less than what I added, or the total number. Okay, so right, so remember this EQ method, and I said it's it's done alphabetically, so you remember EQ, Q comes before X, so always write your equation first. So in other words, this equation, that's the equation, this is the expression down here, Ks equals 2. So always equation first, then expression, then calculate. And you're much less likely to make a silly error if you do that. And then always double check your calculations, because it's so easy to say take the cube root before you've divided by 4, or you've done a square root instead of a cube root, or those sort of things. It's so easy to do, and as you've seen in my slides, I often have made mistakes myself. Okay, now when you have a common ion, you cannot use the shortcuts of Ks is equal to S squared or Ks is equal to 4S cubed, because my ions come from different sources. So I had like that pure silver chloride, so my silver ions and my chloride ions were the same, but when I added the silver nitrate, my silver ion concentration was not the same as the chloride ions concentration. Remember, it was 4:1 instead of 2:2. So don't use this shortcut, because it will be wrong. So here's an example. Calculate the concentration of barium ions, which will dissolve in a potassium sulfate solution. Now, if you know the solubility rules, you should immediately go, barium and sulfates insoluble, so my substance is going to be barium sulfate. If you don't know the solubility rules, look at the Ks and what it's relating to. It's barium sulfate, so you know that you're reacting the sulfate and the barium, and you're dealing with that, and not the potassium. Okay, so your expression, okay, so I said use that as a guide, because that'll really help you work out what to do with your equation. So remember what I said, EQ, first the equation. So here's your ICE method. So Johnny, so initial, change, and end. So in the beginning, I had, now we're only dealing with the barium, this equation, but of course our barium ions come from the barium sulfate, and the sulfate ions come from two different sources. So in the beginning, I have, can have lots of barium sulfate because it's not dissolved, and this is the solid. Okay, Caleb, you don't have to use the ICE method. There are a number of different methods you can use. So this is just one of them. So, and in the beginning, I didn't have any barium ions because they hadn't dissolved yet. Okay, so this is like as I'm adding it in the split second that I'm adding it. So I've got lots of barium sulfate solid, but I haven't had any dissolve yet. Okay, but I do have in the beginning some sulfate ions, because remember I'm adding it to this potassium sulfate solution. So if I've got a 1 molar or 1 mole per liter potassium sulfate solution, then remember this breaks up into K plus ions and sulfate ions. And remember, I've got twice as much K plus ions to sulfate ions, but we're not concerned with potassium, we're only concerned with sulfate. So can you see that my initial concentration of potassium sulfate was 1? So it's 1 mole per liter. So these are all, ideally you should do it in terms of moles and not concentration, but invariably we can get away with using moles per liter unless they give you only, say, in half a liter or something like that. Yep, so April, it's K is in group 1, so K has only a charge of +1, so it's K plus, so you can't get K2 plus. You're going to have 2K plus. So a big 2 and then a K positive when you break it up. Okay, now with the change, so remember when we had that, if it sort of goes, if these go backwards or forwards, both of these have to combine to go there, or if this dissolves, one of these will give one of those and one of those. So remember I added this as a solid. So when I put it into the solution, some of it's going to dissolve, so it's going to go towards the right. I don't know how much is going to dissolve, so call it X. Okay, X for unknown. A small, tiny amount is going to dissolve. For every X of barium sulfate that dissolves, I'm going to have X amount of barium ions being formed and X amount of sulfate ions being formed, because they're in a 1-to-1 ratio. Okay, so when it's dissolved and it's now back at equilibrium again, this is the end part, I still have lots of barium sulfate. Okay, it's sitting there undissolved. Okay, why the plus and minus signs? Here it's because some I've very slightly decreased my amount of barium sulfate, because some of my solid barium sulfate dissolved. Here I've very slightly increased my concentration of barium ions, and I've very slightly increased. So it's a plus for increase and a minus for decrease. So good question. Okay, so if I had lots and I subtract a tiny, tiny, tiny bit of amount, I still have got lots. Okay, so I can assume that, lots subtract 0.0000001 is going to be still lots. So that's an assumption, and you do have to actually write those assumptions down. But we say that there's still going to be lots there. Here, we started with 0, and now we've got this tiny little bit that's dissolved. So the 0.0000, whatever it is. Okay? I mean, we don't know what it is. I just know it's going to be tiny. So I'm giving that example. Here, I had 1, and I've added a tiny little bit. So we've got 1 plus that tiny bit. But now if you think about it, because this constant is so small, I'm not going to have very many dissolving at all. So what is 1 plus 0.000001? What is it going to be? Yep, and you're quite right, Caleb. Significant figures will chop it off anyway. So that 1 plus 0. Blah, 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 blah is going to be 1, isn't it? You can't say it'll be 1.00000. It's going to be the same as 1. Okay, so that is our assumption. Our sulfate is going to stay 1 because, as Caleb quite correctly said, the significant figures are going to chop that off. So that's our first assumption, and our other assumption that there wasn't going to be anything there. Yep, so Johnny, at level 3, we only give you values where you can make these assumptions. So our Ks values will never be bigger than 10 to the minus 4. At university, you do things when the solubility is 10 to the minus 3 and 10 to the minus 2, because you can't actually use assumptions there, and you get quite complicated calculations. But at level 3, we give you pretty insoluble substances that you can always assume that you can ignore the X value here, because you can imagine if you have to start squaring and cubing this term, it gets quite complicated mathematically. Okay, so remember the EEC method. So it's equation, then expression. Okay, so you've got to write this down so you know what to substitute. So having written this down, you can substitute now quite easily. X goes in there, and we've assumed that the 1 plus x is 1, so the 1 goes in there. And we know what Ks is because we're given that. So now you just simply solve for x, and that will be your answer. So as an example, as I said, we've done here in potassium sulfate, if we did the S squared method, right, you'll get an answer of 3.87 times 10 to the minus 5. Whereas when we try and dissolve it in this solution, it'll be 1.5 times 10 to the minus 9. Because I've just divided it by 1, so it's the same. But can you see how much less soluble my barium sulfate is when I've got a common ion present? So a lot more dissolved in pure water than would have dissolved in a solution containing a common ion. So Joe, 1 plus x equals 1. Yes, that's that assumption. So we can make this assumption is because x is so tiny. So because x is so tiny, and as I say, at level 3, you'll only be given where x is tiny, you can make that assumption. Yep. So you will always we will always give you values where it'll work. That's for Johnny. So doing the calculations, doing the 1 plus x, you'll get the same answer within the correct number of significant figures by just simply making that assumption. Yep. And so Caleb, as I say, if you carry on with chemistry at uni, then yes, you will get those complicated ones. So, sorry, time is flying, and I wanted to do a few more things, so let's go through this. But please keep on asking questions. True, Johnny, we never had graphics calculators back in the 80s, so I'm showing my age. Calculate the solubility of silver chromate. So silver chromate, I'm now giving you the insoluble salt, and we know it's the insoluble salt because it's also in the Ks given there, so that's nice. But I've given it to you in terms of a 0.1 mole per liter solution of potassium chromate. So it's exactly the same sort of thing. How much will dissolve? So the same thing, remember, always write your equation first. And this is a case now where I have 2 silvers for every 1 chromate. Okay, so in the beginning I have lots of silver chromate because none has dissolved yet, because it's right in the beginning when I've just dumped it in that split second. So I don't have any silver ions present, but I do have chromate ions present because I've got a potassium chromate. So I've got chromates from the potassium chromate, and that's where it is. As I add the silver chromate, it starts dissolving, and some of it will dissolve, a tiny amount, but it will dissolve. So for every bit that dissolves, I'm going to get twice as much silver ions to chromate ions. So I say this is 2x is being formed. So if x is dissolved, I'm going to get 2x there and x of that. So at the end, when it's reached equilibrium again, I've still got lots of undissolved silver chromate. Okay, I've got 2x of silver ions, and I've got 0.1 of the chromate because I can make this assumption. Okay, I sort of had worked it out, and it's still going to be, even within 3 significant figures, it's going to be 0.1. So the x on either side, it's just a ratio. Yes, so we're saying for x amount of this that dissolves, I'm going to get twice as much of silver. The ratio I think you're referring to is the stoichiometric ratio. So for every one of these, I'm going to get 2 of those and 1 of those. Okay. Right. And now, remember, EK method, first the equation, then the expression. So now you write this in here. Now, in the simple method, you double and square it. Okay? That's where you use that formula of k is equal to 4s cubed, or if you did, yeah. What you have to do is the same thing over here. Is a 2x, you have to square it. So that 2x, you square it. So the 2 is already showing the double, and now you square it. That is my solubility product from there. And so the calculation is I've substituted in for these figures, and I get an answer. So I first divide by 4. It's a common error to take the square root before you divide by 4. Divide by 4 first and then take the square root, and you'll get an answer like that. Yep, so the stoichiometric coefficient is the power. Yep, and that comes in under you know, the level 2 equilibria things. I think I covered that. April, you were here last week, because remember when I said the equilibrium constant is the multiplication, is the product of the concentrations. Okay, so it's like Ag concentration times Ag concentration times chromate concentration, because I could write this equation as Ag2 chromate, you know, so silver chromate is in equilibrium with Ag plus Ag plus chromate. So Ag plus Ag plus is 2Ag plus. So if I said Ag plus times Ag plus times chromate is the same as Ag plus squared times chromate. Okay, so if I did it in pure water, just to show the difference, you can see that it is less soluble in a 0.1 molar of potassium chromate. This is, you know, a much smaller figure than the previous one, so there isn't such an enormous change as before. Yep. So sorry, Emily. As I said, I had it up on Ottle, which I did during the holidays, and then I totally forgot about sending an email out, which is why you didn't get that notification by email. Okay. That first lesson is up there in YouTube if you want to have a look at it. Okay, so Joe, you've got the X sorted. I calculated for X there. And you are welcome to have dumb moments. We all have dumb moments. In fact, dumb moments are the teachable moments. If you never had a dumb moment, you would actually never learn anything, because you'd think you're always right. So if you see, you know, you go, oh, where's that? It's now will stay in your mind, and you won't actually do that again. Okay, you now know you will be solving for X. Okay, so here's another one where we've had an A2B salt, now we're doing an AB2 salt. So we have, this is our insoluble substance. Now I didn't put it in brackets after here, Ks, and then in brackets CaF2. I'm trying to show you all the different ways you could get it in the exam. What they've done is they've inserted this Ks value right after the insoluble substance. So you know that this Ks relates to the calcium fluoride. Okay, so remember, first you write that solubility expression, because you can see if you leave out that 2, you're going to get this wrong. So if you write out the equation and you balance it, you know you're going to get that 2 in there. Okay, and if you've got the equation, then you'll be able to, so I'm just going to go forward to the expression, you'll know to square it, because as somebody, I think it was April, pointed out, the coefficient becomes the superscript. Okay. So the same sort of thing here, my solution of sodium fluoride is 0.1, so some of my calcium fluoride will dissolve. For every 1 calcium fluoride, I'm going to have 1 calcium ion being formed, but I'm going to have double the amount of 2x, double the amount of fluoride. Okay, so at the end, when it's reached equilibrium, I've still got lots of calcium fluoride. I've got X amount of calcium, and I've got 0.1 plus 2x. But actually, that 2x is still, even though it's double the amount of x, it's still a very tiny amount, because this is incredibly tiny. So I can assume this to be still 0.1. Okay, so substitute x for calcium, 0.1 for the fluoride. So F minus, is it soluble? It depends on the salt. So sodium fluoride is soluble. All group 1, well, the ones you come across commonly, lithium, sodium, potassium, all of those are soluble. Okay, so if you get given something like this, you just know that the sodium and fluoride is soluble. But calcium fluoride is not, and that's why we're using it. So, but a tiny bit of calcium fluoride will dissolve. Okay, Joe, I covered this last time very briefly. As I say, there are solubility rules you can learn, but generally, if you've got a small charge on a large ion, it's more soluble than a small ion with a large charge. So as an example, all aluminium salts are insoluble because aluminium is a tiny ion and it's got a +3 charge. So it is going to be very strongly attracted to the anions, and water is not going to pull it out of there. Okay, group 1 is only a single charge of +1, so Na plus, K plus, and so on, lithium plus. So they are more, they can dissolve because water is able to tug it out of there. But once you get to group 2, you get to a 2 plus charge. So the charge, it's now going to be more strongly attracted to the anions, and so it won't dissolve as easily. Now I did talk about a large, there's a difference between single ions and polyatomic ions. That's why sulfates, for instance, tend to be soluble, but carbonates are insoluble, because carbonates are smaller with a 2 minus charge, and sulfates, I mean sulfur with 4 oxygens around it is quite a big, bulky anion, so that they tend to be soluble. Nitrates tend to be soluble, so the NO3 compared to CO3, same thing, but you've got only 1 charge on a nitrate and a 2 charge on a carbonate. So the lime water is just an incredibly dilute solution of calcium hydroxide. Now calcium hydroxide is insoluble, but when we say insoluble, a tiny bit does dissolve. Okay, so this whole X thing, so that's why we talk about sparingly soluble, because when we say, we tend to say it's insoluble because we know not much dissolves, so you won't get a nice concentrated solution of it, but it's often there's sufficient enough there to do what you want. It's like this whole fluoridation of water debate, is the 0.1 or whatever the concentration is it dangerous for you or not? Because all medicines and whatever, the difference between something that kills you, a poison, and a medicine is the dose. So even things like calcium hydroxide, a tiny bit will dissolve, and that can be enough to do the lime water reactions. Okay, now John, the temporary dipole moments, that applies more to molecules rather than ionic substances. I didn't note when that came up, so I'm not too sure. Okay, so here we just solve for x now. This is simpler because we don't have 2x anymore, so we don't have to do any square roots, and so it comes out with that answer. And if I compare it with pure water, you can see, because I didn't have to square it, that it's a lot less soluble than it is in pure water. I do have 2x, but for the fluoride. And because I had 2x for the fluoride, and my common ion was fluoride, I can ignore the 2x. Because the fluoride, I can assume to still be 0.1. Because if you add, the 0.1 plus the tiny bit of fluoride that comes from the calcium fluoride, it's still going to be, with the right, 3 significant figures, 0.1. So Joe, does that make sense? Okay, so what I'm saying, for an AB salt and for an A2B salt or an AB2 salt, it all depends what the common ion is. Here the common ion is the same as the the B2, for instance. Okay, so you don't have to square it. But if the common ion was the calcium, so if I had to say in a calcium chloride solution, so say this question was in a solution that contains 0.1 of calcium chloride, then I only look at the X over here, and I have a 2X over there. Yep, so you assume the common ions concentration. Because what you do is you go, right, if I've got my calcium fluoride, thinking of my calcium ions and my fluoride ions, how much calcium ions have I got? Where did they come from? How many fluoride ions have I got? Where did they come from? And remember, the fluoride comes from two sources, from the sodium fluoride and from the calcium fluoride. So we've got those two sources. And then we just have to work out the final concentration for it. And as I say, at level 3, it's dead easy. You always assume that you can ignore the bit that's dissolved, so the bit from the insoluble salt. Okay, so so you can, as I say, you're always going to achieve level question where you just use that Ks is equal to S squared or something like that. Then the questions we've gone through are for merit and excellence, okay, because you can see there's a lot more thinking there, isn't it? You've got to think, where does this come from? Can I assume, what assumptions can I make? So you can see there's a lot more thinking, okay? The next type of calculation you can get is, will a substance precipitate if I mix two solutions together? So, for, say my calcium fluoride, if I mix a calcium chloride solution together with a sodium fluoride solution, will I get a calcium fluoride precipitate? So my substances are not in equilibrium yet because I'm busy reacting them, and so we talk about an ionic product. Hi there. So wave, you may have some of your students over here. So this is Alison. She also teaches level 3, so if anybody's got Alison.
Familiar names there. Caleb Brand, I'll presume, in April. So I sent April.
Oh, hang on.
Hi everybody. April, I was just saying that I sent an email about not doing scholarship tomorrow, but I'll see you next week. Anyway, good to see you. Have fun. I've got to go, but I'll catch up tomorrow.
Okay. Right, sorry about that. Anyway, it's always nice to see another teacher instead of just a thing. Okay, right. So what you have to do here is you have to work out what would happen. So when you mix these together, where is that position going to be? So it's like that silver chloride, we added something, is it going to shift left or right? So we call this, instead of the solubility product, because we only use that term when it's in equilibrium, so the solid is in equilibrium already with its ions, we call it an ionic product if we have something that's not in equilibrium. And as I say, for solubility, to be in equilibrium, it always has to be a saturated solution. So as an example, lead chloride, okay, my Ks value, I can write the solubility product expression. If I have my lead chloride present in solution, in a saturated solution, and it's in equilibrium with its ions. Okay. My ionic product is done in exactly the same way. The only difference is I can't assume that this is an equilibrium. Okay. So, but it's done, you work it out in exactly the same way as you did the Ks. So, let's do some examples of how we would use this. If your ionic product is smaller than your Ks, then you won't get a precipitate being formed. Okay, because it just means I don't have, because remember what your RP is, it's your solid in equilibrium with your products. So if the RP is smaller, I've got fewer products. So I've got fewer ions in solution. If I've got fewer ions in solution, will they precipitate out? No, because I've got fewer of them, so they're less likely to collide and and start precipitating out. So if my IP is smaller, then a precipitate won't form. Okay, if my IP is bigger, so it means I've actually, when I've added my two solutions together, if I've got a bigger concentration of my ions, then they're going to collide with each other, precipitate out until that equilibrium point is reached. So when my IP has reached my Ks, it's a saturated solution. If my IP is smaller than my Ks, then it's unsaturated. I hope this is clear enough to see if it's too small or not. So if my IP is small, then no precipitate forms. In fact, more solid, if I have any, is going to keep on dissolving. If I have my IP is bigger than my Ks, I'm going to get a precipitate, and not all my ions, but I'm going to have my ions in solution combining together to form my solid. So I'm going to get my position moving to the left when my IP is bigger, okay, and I'm going to have my position moving to the right when my IP is smaller. So a typical question is going to be something like this. Will a precipitate form if you add a solid of this or two solutions or something like that? So here we've got a Ks value, and you know it relates to calcium carbonate. You get given sodium carbonate. So carbonate is your common ion, okay, CO3, that you, or not your common ion, this is going to be your source of ions for the calcium carbonate. And you've got calcium ions. It didn't tell you what. They didn't say calcium chloride, they said calcium ions. So here's your source of calcium ions. So this is going to be the concentration of calcium ions, and this is going to be your source of carbonate ions to form the calcium carbonate. So remember what I said, EEC method, whenever you start, is write down, is they always look to see what salt it is, because the equation you write must be related to the insoluble salt. So if you don't have the right equation, you're going to go wrong. So look for what's the insoluble salt and write the equation down. Yep, so April, this will be the reverse reaction where you get given calcium ions, you get given carbonate ions, and you want to work out, do I have enough of them to form a solid, or will it stay in solution? That's what we're really asking. Okay, so once you've done the equation, and it's always the equation of the insoluble substance or sparingly soluble substance. Once you've got that, you do your expression, because now you know your ratios, you know whether you've got to square them or not. And remember, hopefully you will see the ratio of 1 calcium to 1 carbonate, so you should be able to see that. I know some students, they get confused, they look at that and then they start using that 2 for sodium, in this equation. Can you see there's no sodium in this equation? So that 2 over there is not important. The sodium ions are just going to be sitting around doing nothing. Okay, they're spectator ions. So always go in for the sparingly soluble and look at the ions that make that up. Okay, now you've got to work out the concentration of the calcium ions and the concentration of the carbonate ions. Spectator ions usually cheer or boo or cry, depending on what's happening. So these can be quite complicated, because can you see you get given a mass here? So from the mass, you're going to need to do the molar mass and get the moles and get the concentration and so on. So I strongly recommend that you divide it into sort of like 2 things, each for each ion. So in green, I've done everything relating to the carbonate ion. Okay, the one in blue is relating actually to both, because that in orange is the calcium ion, and the one in blue is really for both, because that's my volume for both. So the calcium ion, I get given the concentration straight away. So that's fine. I can just bung it in, because I'm not going to be changing the concentration, because I'm not changing the volume. Remember, when you mix two solutions, say 250 mils plus 250 mils, I'll end up with 500 mils mixed together. So do my concentrations change then? Yes. So always look to see, has my volume changed? If my volume hasn't changed, it was 250, it's going to stay 250, and it says they assume no volume change, just to spell it out. Then you know you can just insert that orange value in for calcium straight in. Carbonate's a bit more tricky, because you get given a mass, a molar mass, so you have to work out the moles and then use the volume to work out the concentration. So here we go, we've worked out the moles, then you work out the concentration, and there you go. Now that value you have to insert in here. Okay, you don't have to square it or anything, because it's a 1-to-1 ratio. So now we calculate the IP. Notice it's IP and not Ks, because it's not an equilibrium. And we just put in those values, we calculate it. When we've done that, we compare this IP with the Ks. Is this bigger or smaller than the Ks? Okay, right, it's bigger. Good question, April. So why does it say K is at the equation? With over here, it's, I mean, you could have made this, it's just, if you've got the expression down, because remember the IP expression is the same as the KS expression, so if you just sort of like follow the EAT method, at least if you follow the same sort of method, you're less likely to make errors, and that's why I haven't changed this. But notice when I substituted, I did use the term IP. But yes, you could have gone straight away into, EIK. You could have done that, it's still alphabetical. But yeah, so you're welcome.